Hello everyone, we're going to go through the solution to the practice quiz. The first question there is about the knife going through the target. And so we'll start off by drawing a picture. Draw our knife right there. Doesn't have to look like a knife. V1I. We'll call the knife Object 1. Since it looks nothing like a knife. Actually drew it looking more like a knife when I did it on paper, but on this it's just a little bit harder to draw. So V1I we can say is 38.0 meters per second. We'll make that positive, and we'll say to the right is our positive x direction. Okay. Velocity and momentum are both vectors. We've got a target here, and the target is moving to the left. We'll call that object 2. V2I is equal to negative 2.15 meters per second. And this is all part of the initial. And then final is right after, sorry, that's just one L. Right afterward, we've got our target, which says is stopped by the impact. So the target was moving to the left, and amazingly the knife was able to slow it down just enough so it stopped, but so it didn't start moving back in the other direction. And then here's our knife, V1F, and it's moving to the right, but presumably slower than before. And so now we can apply our conservation of momentum equation, which says that if we add up all of the momentum in the system prior to the collision, it should be equal to all of the momentum in the system after the collision. And the reason this is true is because there's no net force acting on the system. If there had been a net force acting on the system, then we would have to include that. But the only forces acting on these objects are the normal force, the force of gravity, and the force of them pushing on each other, which is an internal force. All right, and we know that this is 0, and we can divide both sides by m1. And so then we get V1F equals, and we can convert these to grams, or convert them to kilograms, or we can leave them in grams. It's up to you for this part. You can try it both ways, and you'll see that it comes out the same either way. Okay, we're going to get gram meters per second here, gram meters per second here, divide by grams. So we're going to get units of meters per second. And this comes out to be 9.33 meters per second. And that's positive value, so that means it's moving to the right. And indeed, as we predicted, it's moving slower than it was before. All right, now we can move on to part B of the first part. There we go. How much kinetic energy was lost? So what we need to do is figure out how much kinetic energy was there at the beginning. So that's the kinetic energy of the first object. This is the kinetic energy of the second object. And we just add them together. We do need to work in kilograms here so that we can get units of joules. Make sure you put the squared outside the parentheses. And convert this to kilograms as well. And now when I enter this into my calculator, I don't put this, you don't have to put this in. You can, but if you put the negative sign in, make sure that you have your parentheses and that the squared is outside the parentheses, because when you square a negative number, you're going to get a positive number. If you're not careful, then you just put times negative 2.15 squared with no parentheses, you're going to get the wrong value. So this comes out to be 16.9 joules. And then we do the same thing for the final. So 1/2 m1 v1f squared plus 0. There's no kinetic energy for the second object. And then we just do this for the first object. And we get the kinetic energy of 0.979 joules. And we can say 16.9 joules minus 0.979 joules. And we get 15.9 joules of kinetic energy lost. Alright, and that's our answer. Box around that. There we go. Alright. Now, problem number 2. We have a toy car that is moving at 3 meters per second. So, going to the right. So VI equals 3 meters per second. I didn't put V1I because there's only one object here. And then afterward, it's going to the left. So VF is equal to 2.5 meters per second. Now we need a positive and a negative direction here. So we'll say to the right is our positive direction. So that makes this positive and this negative. So what's the momentum of the toy car before the collision? Well, we know momentum is equal to mass times velocity, where momentum and velocity are both vectors. Scratch that. 1.5 kilograms times 3 meters per second. So that's positive 4.5 kilogram meters per second. And what's the momentum afterward? Same formula, but we put in 1.5 kilograms and negative 2.5 kilogram meters per second. And we get negative 3.75 kilogram meters per second. Is momentum conserved in this collision? And how do you define the system? Well, there's two different ways to think about this. One, the system is the car. Okay, in which case we say, no, momentum's not conserved because the wall exerts a force on the system. Okay, and we can see that the momentum before and after the collision are different. But we could make this system different. We could define the system as the car, the wall, and the entire Earth and all the stuff on it. In which case, we would say yes. Okay, and this, if you had answer 1, that's perfectly fine, but there's just pointing out that there's a different way to look at it. And so if we look at the whole Earth and everything, including the car, as the system, then yes, momentum's conserved. Momentum's conserved in all collisions as long as the net force is 0. The net force equals 0 for this system. Okay, it's hard to do the calculations for this. We could make some attempt at that, but it's certainly a more complicated and just a weird thing to think about. But if we make the whole Earth the system, then the car pushes on the wall, which is connected to the Earth, and the wall pushes back on the car, and so then those two forces are an internal force, and so that makes the net force equal to 0 for the system. All right. Is the average force applied to the car? If the average force is 25 newtons, how long did the collision last? And so we say impulse we know two different ways to think about impulse. One is that the impulse is equal to the change in momentum, and we also know that the impulse is equal to the net force times the time. So change in momentum, we always do final minus initial. So final, negative 3.75 kilogram meters per second, minus the initial 4.5 kilogram meters per second, equals 25 newtons times delta t. Now here, if we then go and divide both sides by 25 newtons, we see that in the numerator here, we're going to get a negative number. A negative number divided by a positive number, that's going to give us a negative value for time. And that's going to be a weird thing. So we don't want to get a negative value for time. So perhaps we missed something. This 25 newtons, that is the magnitude of the force. And if we think about this wall being here, the wall is going to exert a force on the cart in that direction. So the force is actually going to be negative 25 newtons. Okay, so this all makes sense. We put in the negative 25 and we get a value of 0.33 seconds, not repeating. It just ends at 0.33. And so to have 3 digits, we would actually put 0.330. All right. If you have any questions, feel free to follow up with me.